right. My name is Andy Gelman. I'm the co-director of the Scott Institute. And I know you've been here all day, but welcome in any case. So today I have the pleasure of introducing Dr. Brian Anderson. I've known Brian for quite a long time. He's a fellow chemical engineer, got his undergraduate degree at West Virginia and then a PhD at MIT. And when he started in West Virginia as a professor, he was doing all kinds of simulations, going all the way from atomistic scale simulations to reservoir simulations. He was there for something on the order of about 10 years as a professor, and very recently, as in on January 1st, stepped into the role as director of NETL. Brian is a man of very many talents. I will tell you one quick story about him, because he can't do much about it. One day I was at a wedding, got there late as usual, so I'm sitting way in the back. The guy who's singing steps up to the mic, and I'm thinking, it looks a little familiar. Looks a little like Brian Anderson. And this guy starts singing Ave Maria, and I'm thinking, oh, well, no way. Anyway, he's done, wedding's over, Brian Anderson walks up. Believe me, an opera quality voice, in addition to the talent that you will see when he talks to us today. So Brian, all yours.
Well, Andy, thank you. And he asked me before he came out, he says, anything off limits? And I said, no. And I had no idea he was going to share that story, but I really appreciate it. Thanks, Andy. And I'm very grateful to the organizers of CMU Energy Week here at CMU to allow me to come and if you'll indulge me as the audience, to talk about the National Energy Technology Lab and where we're going and some of the truly exciting innovations that are coming out of the lab. And so I just thank everybody for sticking around. The title of the talk is about powering innovation and emerging energy technologies, but I just really want to try to tell you a story about that hidden gem that is one of the 17 Department of Energy national labs that's right here in the backyard of Pittsburgh. We have the three sites, three laboratory sites, one in Pittsburgh, one in Morgantown, West Virginia, and one in Albany, Oregon. And we are largely focused on fossil energy technologies, but as you'll see, true innovation that occurs in laboratories has cross-cutting effects to where all of those technological advances that we're working on in the lab at NETL have applicability across our entire energy landscape and maybe even a little in healthcare as it turns out. And so I'm going to start first with what the priorities of the Office of Fossil Energy are today. And these priorities are not hiding from the fact that one of our Earth's greatest challenges is what we're going to do about the emission of carbon dioxide. And so, as the Department of Energy, as the National Energy Technology Laboratory, we're trying to find technological solutions, innovations to try to tackle these problems. And the laboratory has a long history of doing just that. The Pittsburgh site started over 100 years ago, actually on CMU property. The Morgantown site started 75 years ago on West Virginia University property, and the Albany site started about 75 years ago as well as part of the Bureau of Mines. And over that long history, the innovations that have come out of NETL have truly changed the daily life that you have. And I'm not overstating that. During the response to the Clean Air Act in the 1970s, it was NETL researchers and technology being developed through that laboratory. It wasn't called NETL at the time, but it was those technologies that helped us develop commercialized technologies to be able to mitigate the emissions of criteria pollutants and then of mercury. And so it is truly NETL commercialized technology that is removing mercury from our air that we breathe every day. You may not see it, you may not know it, but it's certainly had an impact. And then 30 years ago, it was research that was done at the laboratory and with partners, the Gas Research Institute at the time, that developed the next generation technology for horizontal drilling and hydraulic stimulation, that those technologies now have been commercialized tens of thousands of times over, that has completely changed the landscape of the energy environment globally. And again, that's not overstating. The entire landscape of OPEC's hold on the as a the hold on the oil sector, the balance of energy trade from the United States has come from those technologies developed out of NETL. And so we're going to change the world again. And that's where we're going. So not any lofty goals about where I see NETL going in the future, but the one priority, the top priority right now within the Office of Fossil Energy is to develop the coal plant of the future. And that coal plant of the future doesn't look like what we have on the market today. It's not the megalith 1 gigawatt size power plant. It's the type that can integrate into the renewables that are being deployed into our energy sector, that it's flexible, it's innovative, it's integrated, it's resilient, it's small, and it's transformative. That, if you followed all the letters, that is Coal First. And so we launched a program late last year called Coal First to challenge the industry, the design and engineering industry, to come up with from a blank slate, what does a coal plant look like that meets all of those criteria? And first and foremost, it means that those coal plants of the future have carbon capture integrated into the design from the beginning. And so that we can push the efficiency, we can push the carbon footprint of coal plant of the future down. Now, one might say in the United States, those coal plants of the future might not have the market to deploy because we do have a relatively flat electricity load, at least as it is today. The more vehicles we electrify, that might change. But the rest of the globe is going to need energy. And so if we can develop those technologies here and be able to export those to the 1.2 billion people on the planet today that don't have the type of access to electricity that we do in the United States, or the 400 million people in India that Prime Minister Modi says he needs to electrify. If we can develop those technologies that are ready for carbon capture, ready for the lower carbon footprint, then we'll be in a much better space. And so in the near future, you'll see some announcements about the Coal First program. To move a little faster, the other priorities is modernizing the existing coal fleet. There's $1 trillion of existing coal-burning power technology in the market in the world. And so all of that sunk capital, if we can find ways to increase the efficiency and mitigate carbon from those existing fleets, we can have a better impact on the economy. And it can fit within this portfolio. If you were here earlier, I'm a firm believer that in order to tackle that challenge, we need a full portfolio. And so we need to develop technologies for the fossil fleet. The third is reducing the cost of carbon capture, utilization, and storage. Do you see a theme here? And that theme is we are part of the solution. And in order to do that, we have to reduce the cost of carbon capture from $50 a ton to $30 a ton is a target. A fourth area is in advancing big data, or expanding the use of big data. Right now, we've heard a couple times throughout the day today about the use of artificial intelligence, big data analytics, and machine learning. And I'm really excited to be here at CMU, where there are so many experts in this space for us to collaborate with. And so I feel very comfortable for us to be able to move forward big data, artificial intelligence, and machine learning into the energy space to where it has deep penetration to tackle all of our challenges and meet all of our goals. The next to last, the penultimate fossil energy priority is at that energy-water nexus. The impacts of climate, the impacts of air emissions is not the only impact we have in our energy sector. In the environment. And so we need to minimize the impact to our freshwater resources because it is the next critical restriction on being able to feed and provide clean water to the projected 10 billion people on the planet. And then the last priority is how we monetize and how we use the Strategic Petroleum Reserve for the best impact of the American citizens, because we have innovated our way into excess oil, and the legacy of the Strategic Petroleum Reserve should be utilized best for the citizens. So all of those priorities fit within the mission of the laboratory, the National Energy Technology Laboratory. And the key words of our mission that I want you to take away is that we are discovering, integrating, and maturing technologies to move them into the marketplace. And the reason I focus on that, discovering, That's early stage research. How do we find the next discovery, the next innovation that is going to be able to change the world? So we try to discover that through two different prongs at the laboratory. One is through our federal role of managing a portfolio that's 900 research projects and a combined portfolio right now of about $6.6 billion of research that we're managing. And so we want to look through those 900 projects and find the next key technology that's going to change the world. Then how do we integrate them? The energy system is a very integrated system, not just the grid, but our transportation infrastructure, our fuels infrastructure. How do we then take all of the innovative technologies and be able to integrate them into a system so we can mature them and deploy them? And so the focus of our entire portfolio of research, whether it's in-house at the laboratory or through our 900 extramural partnerships, our goal is then to be able to take those technologies and see them into the market. And that's the role of an applied lab. Of the U.S. Department of Energy, the 17 labs, 10 of them are from the Office of Science, Fundamental Science. That's where our big synchrotrons and our light sources are. 3 of us are applied labs. And those 3 applied labs are in fossil energy, energy efficiency and renewable energy, and nuclear energy. And so it's our job to make sure within those sectors that we're pushing technologies into the market. And so our vision is that we are the world's renowned resource for fossil energy technology development, and I think we're pretty close to being there already. And we have at our disposal within the laboratory 6 major core competencies, and these core competencies are in computational engineering. We are home to one of the world's fastest supercomputers. It happens to be in Morgantown, and we're actually in the middle of building and constructing a facility specifically dedicated to machine learning and artificial intelligence. It's built from the ground up with the hardware and the software infrastructure to be able to access large data sets and apply new machine learning and artificial intelligence algorithms that I'm hoping that researchers across the space, including at CMU, can help us test and put onto that system. We also have deep roots in materials engineering and manufacturing. As a matter of fact, our facilities in Albany, Oregon are some of the world-class facilities that are not seen in any other type of material and alloy development and processing facility in the world. And a whole ecosystem of advanced materials and alloy development has sprung out of and spun out of that laboratory in Albany. And not to mention our ability to do computational prediction with our researchers in Morgantown and Pittsburgh. The third core competency is in what happens under the subsurface. And that obviously, or it may be obvious that includes carbon sequestration as well as recovery of natural gas and oil resources. The fourth core competency is in energy conversion. How do we develop, again, that coal plant of the future? How do we convert energy from its primary source to our usable source, would be an electron or possibly a hydrogen molecule? How do we convert that energy system? And then the fourth technical core competency, or fifth technical competency is in system engineering and analysis. When I mentioned that our goal is to deploy technologies into the commercial space, we have to understand the commercial space and how technology can deploy in that, and we do that through systems engineering analysis. And then the sixth core competency is how we integrate the program. Again, back to the $6.6 billion portfolio of research across 900 projects, we think that we're one of the world's experts in how to take and manage a very large research portfolio and create an integrated solution. But we are within a very specific region in the United States. If we look at the US and we break it up into all of its regions as defined by the EIA, and we look at this Mid-Atlantic region, there is a tremendous output of energy and technology and innovation in this Mid-Atlantic region. If we layer on the sedimentary basins of our oil and gas, the tight oil and gas plays, our coal fields, we have a number of coal power plants, and it's a decreasing number as we speak. Natural gas plants, there are 40 of them that are in various stages of permit in Ohio and Pennsylvania. We do have petroleum power plants, although not very efficient. We do have a nuclear fleet. We have lots of renewable power generation in wind, in solar. We even have some geothermal resource. If anybody knows my background, I know a little bit about that. And we have hydro in this region. Overlaying this is the entire grid infrastructure across the PJM interconnect, as well as actually a couple interconnects are represented here. We have extremely strong academic partners, and the two largest NETL laboratory facilities are right here in this Mid-Atlantic region. So call me biased, but I think that 100 years ago, when we were first, well, it was over 100 years ago, but when Nikola Tesla was doing work at Westinghouse, we in this region created the grid of the 20th century. And it's now on us in this region to help create the future energy of the 21st century. And so I think we're well positioned to do that. So we do this through partnerships, not only the universities, but industry partnerships, academic partnerships, the non-government partnerships, the government partnerships across this region, because no one entity can do it alone. But if we're all working toward a common goal, and that is maybe my two and a half year old's future, or grandkids' futures, then I think we can achieve that. And so the pathway that I wanted to talk about and some specific examples of projects and innovations that we're working on within the laboratory are in power electronics, and of course that spans across the grid, agnostic to its fuel type. Energy conversion, some really unique and new changes to how we convert energy into its useful, from its raw material into its useful energy. How can we leverage coal as a hydrocarbon resource, not just as a thermal power resource, to help innovate the new products of the future and high-value products from that coal resource? And we use multi-scale computational science techniques to be able to manipulate the properties of materials from a fundamental level all the way through how those materials act at scale. And then finally, advanced materials and how we can create new materials that help us overcome many of these challenges. So I'll give an example of these. This particular set of projects is how we create and manipulate the alloy materials at the nanoscale. And this is an effort that's a collaboration between Carnegie Mellon University, NETL, Eaton, NASA Glenn, and North Carolina State University. And we have some really star researchers in this particular space of how we can create new power electronics from alloys, as I mentioned, with specific nanostructure and microstructure, and control that through the way we process the alloy material. So taking the manufacturing of the last century and development of materials and alloys and moving it forward by controlling that nanostructure through, well, one specific example in here is strain-induced strain annealing, where you can induce nanostructure, so not beyond the grain boundaries of microstructure, but nanostructure that can then create the much higher efficient power electronic materials. And so while depending on the background of the audience, what that really means is we can take a DC to DC power converter that, some people it would be a step-up voltage or a step-down in voltage, take that and shrink it, make it more efficient by factors of 20 and 30%, shrink it by a factor of 2, so that when we deploy solar arrays into the field, the power electronics that accompany that become much smaller, much cheaper, much more efficient, and we remove all the inefficiencies out of the grid. So we can shrink we can shrink a large transformer that if anybody is in a neighborhood knows the big green box that's a little smaller than this podium, and we can shrink it into something that might fit in a lunch box. The efficiencies associated with that greatly enable microgrids. They enable the ability to create a more resilient grid and one that is much more efficient. And so that's this particular set of projects won Carnegie Science Awards, has been patented, and then right now is in the process of deployment, both from Met Glass and their ability to cast it, as well as Eaton testing these. And so this is something that's moved forward very fast. And from the theme, another theme that I'd like to impart upon you is that our goal is to be able to take technologies, instead of a 30-year lifespan of taking a technology and putting it into hydraulic drilling and fracturing, how much can we shrink the commercialization of technology, the timeline for that? So a second example I want to mention is how we can optimize reaction engineering science. So this is core to, indulge the chemical engineer who's up here, where what we're trying to do is identify new ways of intensifying reaction processes so that we can, again, be more efficient, more targeted on conversion of materials and enable the tapping into of the prolific natural gas reserve that we have. How can we do, in a sustainable way, take natural gas and convert it into our products that we use every day, be it a fuel in a vehicle or fertilizer or ammonia. And so this particular facility we invested in, it's at the Morgantown site, and it truly is one of a kind in the world in its ability, and I guess the laser pointer is not going to work, but we know of no other facility like this in the world that can be able to tune almost every aspect of a chemical reaction in a fairly large-scale facility with 24/7 unattended operation, so we can cycle through thousands and thousands of different scenarios of how to optimize a chemical process. And so we're really excited about this facility. And one specific example is how we can then use microwave technology, which, of course, when I was a kid, I remember our first microwave was a pretty big behemoth of a thing. So that means that that microwave technology has been around for a while. But what is new is our ability to tune the frequency, to tune the power, to be able to target very specific reactions where if we start with a molecular level atomistic modeling of a reaction, we can then tune the excitation energy of that particular reaction so that we have the actual desired products that we want. And so, again, big picture, what does that really mean? Well, it means we create less waste. It means that we have to do less separations in an industrial process at the end, which all of this comes back to reducing the energy footprint of our industrial processes across the manufacturing space and create new opportunities to utilize the resources that we have. And so we have a couple examples of projects, and I wanted to highlight that these were not funded through the Fossil Energy Department, just to give you a little insight into the laboratory. We do work for ARPA-E and for the Advanced Manufacturing Office in this particular program. Another exciting area is in how we add value to our coal resource. And again, this is how can we use this basis of a condensed carbon material to start creating value-added products. And these value-added products can be everything from graphene as a very functional material with lots of interesting electrical properties. Many of you know a lot more about graphene than I do, and maybe a couple of you less, but it's an exciting material that has extremely high strength and very interesting tunable electronic properties. But then, what about creating the next material of the future that is a carbon fiber reinforced plastic? And how can we then integrate carbon fibers into our plastics manufacturing to start the replacement and lightweighting of vehicles, the replacement of the steel framework and parts within the automobile? So as we move to a more electrified fleet, an automated fleet, we need these vehicles to be as light as possible so that our battery life and our range can be as long and as far as possible. And so there's been tremendous efforts in lightweighting of vehicles to date, but I think as we develop new, stronger materials through innovation of these new carbon fiber reinforced plastics, as well as the ability to 3D print and use advanced and additive manufacturing capabilities, this will enable and open up a whole new world of possibilities. And one example of that type of material for it to be used, a CFRP can be used as a bridge wrap for the bridge supports that we have an estimated across Pennsylvania and West Virginia 10,000 or so bridges that are in desperate need of repair. And what better way to do that with a material that can have the strength of steel but be a third of the weight and flexible and has the ability to wrap the bridge pillars or create new bridge surfacing. And so the beneficiation areas of coal are in coal to different carbon products, how we upgrade the feedstock and create a better, more efficient fuel, as well as assessing the properties of the existing coal resource so that we can tune the resource to its application. Another, what I think is a truly innovative and exciting area is in the computational modeling efforts. And so we have one effort called IDEAS, which is a collaboration of a couple universities you see and national laboratories that is specifically around how we design, again, the coal plant of the future. But it's not just design that we used as engineers in the past. It's how we then take the modeling effort all the way from the molecular and predictive scale up through scaling it up. And why this is important is because we want to get over that lead time, that 10-year lead time, or in some cases 30-year lead time of moving concepts to market. And so if we can leapfrog the scale up of new systems, if we can leapfrog that scale up, we can in fact shorten the development time frame. And if you're here for the earlier panel, when Granger Morgan was challenging us, how quickly can we get these to market, this is exactly the focus. How can we use modeling and simulation and all of our newfound computational power over the last 15 years and use it to try to take technologies and move them into the market much, much faster so we can tackle this challenge in the near term. And so one component of this tool set is something that is in the computational fluid dynamics realm. And so our code at NETL, this is one of our software solutions. It is open source because we're a government-operated laboratory. And so it's an open source code that is one of the leading multi-phase fluid codes in the country. And to give you an insight into how that truly impacts things, is there is a nuclear liquid waste treatment facility in Idaho that during startup, it was supposed to be a fluidized bed, and during startup was having some trouble in fluidizing the large-scale facility. And so they called upon NETL and our experience and our expertise in multi-phase fluid flow, and our researchers were able to identify the appropriate conditions under which that reactor was not going to work and start up, and be able to redesign that reactor on the fly. Now, the true ramifications of this was it saved about $10 million in trying a bunch of different scenarios with the real reactor. But the key was then it saved hundreds of millions of dollars through a few month effort computationally. It saved hundreds of millions of dollars in delays of startup of this particular reactor. And so that's just an illustration of how we can use computation to be able to shorten that time frame and create the opportunities for scale up in a much shorter time frame for new opportunities that aren't just limited to the fossil energy space. And so our computational tools span time and length scales, again, all the way from the molecular scale to the entire electrical grid of the United States, as well as in time scale from the nanosecond to years. And so the key thing in ideas is how we bridge the gap and be able to have true impact in modeling across the scales. A couple last examples I want to give of just exciting innovations that we have coming out of NETL that I think I want this audience to understand. One is in how we design and develop and deploy advanced materials, and you'll see another theme that keeps recurring here is how we use computation, simulation, prediction in order to move materials into the commercial market. And so by using computational tools, starting at the atomistic level, to be able to design new alloys and new ways to process those alloys, we've been able to design and develop and patent and start testing a new alloy with properties that outperform anything on the market. And just as a quick aside, you see NETL CPJ7 as a tribute to those inventors that we have. CPJ are actually the first names of the three inventors of this particular alloy, because this will really revolutionize the opportunities in advanced ultra-supercritical power technologies that will increase and improve the efficiency of the power fleet by about 20% over the existing fleet. And so again, these new alloys, we at NETL are leading a group of national laboratories. You see Oak Ridge, Ames Laboratory, Los Alamos, Lawrence Livermore, Pacific Northwest, and Idaho National Laboratory in a program called XMAT, where this is Materials for Extreme Environments. And if you can imagine the extreme environments in the energy sector that we might encounter, they're high temperature, high pressure, it's in the nuclear space, it's in solar concentrating reactors in the renewable space, as well as in fossil. And so if we can develop those new materials that can withstand those extreme environments, then we can achieve much, much higher efficiency across the board, be it in nuclear or in solar thermal. And so lastly, the last example I want to give you is how we're working to drive down the cost of carbon capture. And I wanted to close with this one because I think that, as some comments earlier on the earlier panel, if we're going to tackle the problem of CO2 in the atmosphere in the near future with capital that can be deployed into the market, we have to have solutions today in 10 years and that can be deployed across the globe in capturing carbon. In the near term, this is what we have at our disposal with our existing fleet, with the sunk capital that's across the globe. And so what we were able to do in-house using our supercomputer named Joule on campus is we ran over 1 million different scenarios from very fundamental physical chemistry scenarios of mixed matrix membranes with metal organic frameworks and polymers to screen out the different types of materials that can be used for membrane separation of CO2 from nitrogen and oxygen and water vapor. And we were able to do that over the course of, now computationally it took about 4 weeks to do those 1 million scenarios on our supercomputer. And the material is showing that we can decrease that cost of carbon capture using membrane technology from about $63 per metric ton to about $48. And this is that first generation. We have now refreshed our supercomputer earlier this year, brought it online, and increased our computational power by about a factor of 4. So a 4-week effort we can do now in a week. And so now as we start iterating and developing those new materials, and we have proven that we can take materials from the computational space and predictive computational chemistry and actually create these materials in the laboratory. And so this is truly exciting for us to be able to tackle these challenges and reduce the cost of carbon capture. And so finally, to kind of close, how can you partner with NETL? And so we have a whole toolkit at our disposal. We have something called a CRADA, which is a cooperative research and development agreement where we partner hand in hand on trying to tackle challenges. And we have a number of CRADAs with entities here in this room, including CMU. Contributed funds agreements are ones where you pay us to do research in case you want to access our technical capabilities. And then if we're driving toward common goals, we can start with MOUs and MOAs. These are just parts of our toolkit of how to interact, but the best way is to just call us. Ask for a visit, come to site, invite us to come out and talk. We have at the laboratory 1,234 dedicated employees across our 3 laboratory sites through our federal research and contractor workforce who are truly all dedicated to tackling our largest problems in the energy space. And we would really be excited and open to work with all of you, the industry and academia. And so I do want to thank you for giving me the opportunity to talk a little bit about NETL. I hope I have exuded some of the excitement that I have about joining what is truly a world-class organization that, when I first took the job and was talking with the Pittsburgh Post-Gazette, I described as a hidden gem. I don't want us to be hidden anymore. The level of talent, the level of competency, and dedication to tackling these energy challenges is truly astounding, and I want everybody in this region and the nation and the world to know what we have right here in the Pittsburgh region. And so thank you very much, and I hope we have some questions.
So we do have a couple of questions. Do you plan to extend your work on carbon capture technology to address natural gas combined cycle technology?
So the development of our technologies that we have in carbon capture are applicable, and we very specifically work all the way from 400 parts per million to natural gas combined cycle technologies, which would be at around 4%, and then 14% for our coal system. So we are specifically developing technologies that can work across all of those different scales. And so that addresses some of the challenge of natural gas is its lower concentration, but it also doesn't have the contaminants. So.
Okay, next question. Is NETL doing work to lower the cost of coal production, especially in Appalachia?
So what's really interesting is our portfolio development. On the coal side, and this is mandated by the line items that Congress appropriates of how we are supposed to spend the research dollars. In coal, it's basically everything from after you deliver coal from a train to something. And so we don't really touch mining, even though our history started with the Bureau of Mines and was largely about safety. And so that was a long answer. The short answer is that's actually not, Congress doesn't let us or tell us to work in that space. Yeah.
Does research with the carbon capture alloys have applications outside of energy?
Yes. And so one example, and I did allude to it and I forgot to mention it, since we do have this fundamental capability of developing and predicting alloy properties from the composition as well as the microstructure and the way it's produced, that has already been applied to many different other spaces. And so in fact, we own a patent on one of the leading biodegradable metallic heart stent materials that I hope nobody in here is wearing that technology, but in fact, because of that skill set, yes, it's applicable in biomedical applications, including for joint replacement, scaffolding, for the application of stem cell regeneration, where you can create the scaffold from biodegradable materials.
So a question similarly about the DC grid. More wire will be needed, so could you use that material for DC grid?
Can you say that again?
DC grid will be more needed in the future. Are you working on those types of new wire materials?
Well, so in the new wire materials, no, we're not actively working on that. And in terms of the one aspect of the lab, the systems engineering and analysis group, we are working very closely on developing the types of deployment models that would include more DC grid, localized DC grid around DC generation capacity, as well as how that then integrates within our largely AC grid. And that would include the large-scale need for long-range, high-voltage DC across the United States. And actually, a colleague from NREL here as well, NREL's doing a lot of work on the grid space and grid modeling.
They keep coming.
Yeah.
NETL has supported work on recovering rare earths and other materials from coal wastes.
Yeah.
Is this a promising way to address critical materials needs?
We are very excited about the progress that we're seeing from that portfolio in the extraction of rare earths from coal waste, from coal seams. As a matter of fact, we just had a review meeting last week with the project teams, and the project teams are seeing just absolute tremendous success and pathways and targets toward commercializing the technologies. Now, when I speak to getting technologies into the commercial market at a faster timescale, the projects right now are on target to start moving and commercialize technologies at record speed, and I really mean that. And we're driving them pretty hard, I have to say. But in terms of the development of the technology, we specifically wanted them to create commercialization plans and the way that we find the pathway into commercialization. So from a technological standpoint, the University of Kentucky has been able to achieve purity of rare earth extraction that greatly exceeded the targets that we had hoped. And researchers at West Virginia University from acid mine drainage sludge has shown the cost of extraction and the ability to make large extraction feasible is really also exceeding our expectations. And so we have a multi-pronged approach. Sorry to go on a little bit about this, but from a national standpoint, from a national security standpoint, from a supply chain standpoint, the access that we need to rare earths and other critical materials is truly a national need. And we're really excited about the technologies that are being developed to be able to get it from the Appalachian region, specifically because the mine, Mountain Pass Mine at the border of Nevada and California, which was the last operating commercial rare earth mine in the United States that closed about 10 years ago, that mine did not have the heavy rare earths that are even much more valuable for use in power electronics, handheld electronics, permanent magnets that we need for our electric motors, for electrifying electrifying our vehicle fleet, for our wind turbines. So I cannot overstate how critical this is and how excited we are about that technology portfolio. Thanks. Yeah, you got me going on that one.
So last question.
Yeah.
What are you most excited about? And I know you've mentioned a couple of things. Most excited about for this role that you're in now, and what would you like for us to know?
Well, I'll start with what I'd most like you to know, and I mentioned it earlier, and I just want to reiterate it, is that for 100 years, NETL has been part of this community, and I could not have been, and so I'm weaving them together, I could not have been more excited about joining what is truly a world-class team. And I want to be able, and one of the goals I have is to be able to enable that workforce at NETL, that 1,234 folks. That's a 2-week-old number, and we onboarded a couple people last week, so it's a little out of date. But is to enable them to be able to do the best science that's possible, and that includes how we integrate the science that's occurring across the country that we're partnered with. And so, what's really exciting about my role personally in this job is the fact that we have 900 partners, that we're all trying to tackle challenges across that are true humanitarian challenges that will impact the globe. And so when we have the opportunity to reach into 900 different organizations and tackle one problem, I think it's really exciting to be here. So thank you, Anna.